So hi, in this video we're going to be simplifying some radical expressions and talk about how that works. So the first example is a pretty easy one. It's asking us for the fifth root of 29y squared to the fifth power. And what makes that easy is that the fifth root just undoes the fifth power and gets us back to 29y squared. If you take anything to the fifth power and then take the fifth root of that, you're back where you started. Okay, what's the square root of 2 times the square root of 50? Well, that would be equal to the square root of 2 times 50, that is the square root of 100, and that would be 10. Now, the square root of 2 by itself is 1.4142 and so on. The square root of 50 by itself is 7.07 something, and you might not guess this from just looking at those two numbers, but when you multiply them together, you do end up with just plain 10. Let's try this one, the square root of 45. Now, what we want to do with this is we want to simplify this. So we are not looking for what the calculator gives us when we ask it for the square root of 45, which is 6.7082, and then really the digits just keep on going forever. The square root of 45 is an irrational number, which means we can't write down exactly what it is in decimal form because the digits just keep on going forever, and they don't just repeat the same thing over and over again. So, for something like the square root of 45, it's not a nice whole number because 45 is not a perfect square. In some situations, we just need to know approximately what it is. It's about 6.7. Or if you wanted to be more precise, it's about 6.7082. But that's not what we're looking for here. Here we want to keep something that's exactly equal to the square root of 45. Now, 45 is not a perfect square. It's not on the list here, so we can't say the square root of 45 is just some nice whole number. But we can break 45 up into 9 times 5. And we do know what the square root of 9 is as a nice whole number. It's just 3. So if we factor the 45 into 9 times 5, then one of those at least is a perfect square. And we can take square root of 9 times the square root of 5 is 3 times the square root of 5. So in a way, we've simplified the square root of 45 into 3 times the square root of 5. And what makes that simpler is that the part under the square root sign is smaller or simpler. We've gotten at least part of this out from under the radical sign. So that's what we want to do when we're simplifying a radical expression. Get as much as we can out from under the radical sign. Square root of y to the 17th power. So a variable to the 17th power is not a perfect square. But if we look for the biggest factor that is a perfect square, that would be y to the 16th power. We can say what the square root of y to the 16th power is. So if we break this up into y to the 16th times y, after all, y to the 17th is 17 y's all multiplied together. So that's 16 of them times one more. And then we've got the square root of y to the 16th, which is y to the 8th, times the square root of y, which just has to stay the square root of y. And this one just puts those last two examples together. For the square root of 45y to the 17th, we can break the 45 up into 9 times 5, break the y to the 17th up into y to the 16th times y, take the square roots of what we can, get as much as we can out from under the radical sign, and end up with 3y to the 8th times the square root of 5y. How about this one? The square root of 300 times a to the 9th times b to the 10th. 300 is not a perfect square, but we can factor out something that is. We can break that up into 100 times 3. a to the 9th is not a perfect square, but we can factor out something that is. The biggest perfect square we can factor out is a to the 8th times one more a left over. And then b to the 10th is a perfect square. We can take the square root of something to the 10th power and just get something to the 5th power. So after we do that factoring that I was talking about, we're looking at the square root of 100 times 3 times a to the 8th times a times b to the 10th. So the square root of 100 is 10. The square root of a to the 8th is a to the 4th. The square root of b to the 10th is b to the 5th. And then still left over underneath the radical sign, we have the square root of the 3 and the a here. Okay, how about a cube root? The cube root of y to the 5th. The biggest perfect cube that we can factor out from y to the 5th. If we want to break this up into something that we can take the cube root of times whatever is left over, we would break this up into y to the 3rd, that is y cubed, times y squared. Y times y times y times y times y. So the cube root of y to the 3rd is just y, and then we're left with the cube root of y squared. Next, we're going to be doing something called rationalizing the denominator. So the idea is sometimes you may have a denominator that is irrational. It's got a radical sign in it. It's something like the square root of 3. And we want to rewrite that as something equivalent, but that does not have a square root in the denominator. So rationalizing the denominator means to get an expression so that it no longer has a radical sign in the denominator or a fraction under a radical sign. So the way we'll do that here is we take advantage of the fact that with a fraction, we are allowed to multiply the numerator and denominator by the same thing. So I'm going to multiply the numerator and denominator of this fractional expression both by the square root of 3. Because really I'm multiplying the whole thing by square root of 3 over square root of 3, which is 1. So multiplying by 1 doesn't change the number. And the reason I'm doing this is because now on top we get 12 times the square root of 3, which doesn't really help us. But on the bottom we have the square root of 3 times the square root of 3, which is just plain old 3. One way to look at it is that it's the square root of 3 times 3, that is the square root of 9, which is 3. Or another way to look at it is that it's the square root of 3 squared. Square root of 3 times itself, and then squaring undoes the square root, and you just get 3. And now I see one more thing we can do to simplify this a bit further. The 12 on top divided by the 3 on the bottom would just be 4 times the square root of 3. So 12 divided by the square root of 3 is equal to 4 times the square root of 3. Now, by the way, this is the kind of thing that you can't really do on a calculator, but you can check on a calculator. So I could reach for my calculator, and first I could ask it, hey calculator, what is 12 divided by the square root of 3? And it gives me this weird irrational number, 6.9282 something. And then I can ask it, okay, what is 4 times the square root of 3? And it gives me that very same number, something that looks exactly the same as what I got before. So looks like pretty good evidence that these two things really are equal to one another. They're just different ways of writing the same number. Okay, let's do another one of these. Let's rationalize the denominator of 3 over the square root of 7. What are we going to do? We're going to multiply by square root of 7 on top and on the bottom. So on top we get 3 times the square root of 7. On the bottom we get the square root of 7 times the square root of 7, which is just 7. And this time we can't reduce it, so that is the final answer. And if you don't think this really looks any simpler than this, well, in one way it isn't, but in another way, in some situations, something like this would be better because it has a simpler denominator. And in some situations, you want your denominators to be as simple as possible. Here's something you could try on your calculator. Ask your calculator to multiply together the numbers 2 plus the square root of 3 and 2 minus the square root of 3. If you want to try this yourself, pause the video. I'll wait, come back, and then we'll see what we get. So I'm asking my calculator for 2 plus the square root of 3 times 2 minus the square root of 3. And it says that that's 1. Who would have thought? Well, what happens if we multiply this out by hand, just using our powers of algebra? Think FOIL method, or just think like difference of two squares. The two things that we're multiplying together are the same as one another, except that one has a plus and one has a minus. So when you multiply that out, you get 2 squared, the first thing squared, minus the second thing squared. If you actually did use the FOIL method, you'd get 2 times 2. On the outside, you'd get minus 2 root 3, and on the inside, you get plus 2 root 3, so those would add up to 0. And then last, you'd get a plus times a minus is minus square root of 3 times itself. So we got 2 squared, which is 4, minus the square root of 3 squared, which is 3, and then, of course, 4 minus 3 is just 1. Now, these two things that we were multiplying together are sometimes called conjugates of one another. That's the word for when you have two expressions that are the same, except one has a plus and one has a minus in the middle. And notice how when we multiplied those together, the result was just a nice whole number. That's going to come in handy in the next example. We're going to rationalize the denominator of the expression 20 over 3 plus the square root of 5. We're going to rewrite that so that it no longer has a radical in the denominator. Now, your first thought might be, let's do what we did last time and just multiply by whatever's on the denominator, multiply by that again, just on top and on the bottom. So if I multiply by 3 plus the square root of 5 on top and on the bottom, on top I get 20 times the quantity 3 plus the square root of 5. On the bottom I get 3 plus the square root of 5 times itself. When I multiply that out, like you could do it with the FOIL method, I get 9 plus 3 root 5 plus another 3 root 5 plus 5, and that's not really going to help us because we still have a square root. We still have a radical 5 left in the denominator. So that's not really the way this works. Okay, let's try something else. What if we just multiplied by just the square root of 5 on top and on the bottom? Well, then we'd get 20 times, oops, that should say just the square root of 5. Sorry, let me fix. So when we multiply by the square root of 5 on top and on the bottom, now look what we get on the bottom. We got to multiply this out with the distributive property. We get 3 times the square root of 5 plus 5. Still no good. We still have a square root in the denominator. The trick is, what we want to multiply by is the conjugate, 3 minus the square root of 5. Because now when we multiply things out on the bottom, we get 3 squared minus the square root of 5 squared, and everything else cancels out, so that would just be 9 minus 5, or 4. Meanwhile, upstairs, we're taking 20 times 3 minus the square root of 5, so if you multiply that out, 20 times 3 is 60, minus, or that should be a minus, sorry, minus 20 times the square root of 5. So now the numerator is 60 minus 20 times the square root of 5. The denominator is just 4, and here we can actually simplify some more because everything on top can be divided by 4. So we can simplify this down. 60 divided by 4 would be 15, minus 20 root 5 divided by 4 would be 5 root 5. And again, this is the kind of thing that you couldn't do on a calculator, but you could check on a calculator. You could ask your calculator to evaluate what we started with and what we ended up with, and make sure they look the same as decimal numbers. So, yay, this time that worked. Now I'm going to end this video here and come back in another video and talk about exponents and ways of writing radicals, square roots, cube roots, and so forth by using fractional exponents instead of radical signs.